Good morning, plant scientists. Today we're going to discuss soils. Soil, of course, is one of the most important factors in agricultural production. So it's important that we discuss as much as we can in the short amount of time that we have. Soil, of course, is the product of many different interactions of the parent material, the rock that gives birth to soil, climate, the topography or slope, and both above ground and below ground biology. And all of this interacts over time to create a soil. And I want you to remember these 5 factors of soil formation. The first 4 being the parent material, the climate, the topography, and the biology, and then time being the unifying factor. Soils evolve over time, and indeed they change much dramatically as a result of our actions. So what is soil? Well, generally we can kind of look at soil as the unconsolidated material that we stand on as well as produce crops on. So it is composed of weathered rock, air, water, decomposed organic material, as well as some that is not decomposed, and of course various organisms, of which there can be millions, if not billions, of micro and macroorganisms in the soil. So first we look at the solid fraction of soil, which includes rock fragments and minerals. Then the organic fraction, which comes mostly from living things, plant and animal residues, as well as the soil biology. Also a liquid and kind of air fraction. So we're looking at water and all the dissolved minerals contained in it as the liquid fraction or the soil solution, as well as air in the soil, pockets of air. All of these factors lead to the ability to support plant growth. When we look at soils, especially the solid fractions, we tend to see in between these solid fractions pore spaces, and these vary in size as well as their continuity and are an incredibly important physical property of soils. If we look at a natural soil or a productive agricultural soil, we'll see that about half of the soil is solid and half of it is pore space. And amongst that, we look at the pore spaces either being filled in with water or air, depending on how much moisture is actually in the soil. An agriculturally productive soil should have about 50% of pore spaces. That way it can actually drain water, but also hold air. This is incredibly important for plant growth. When water drains through soil, what we have left after gravity has removed much of it is called the filled capacity of the soil. And that becomes important later on when we're trying to gauge irrigation for soils. Let's look at parent materials for a second. And generally, the parent material, of course, is the first limiting factor of what creates a soil. And we can see either igneous, sedimentary, or metamorphic rocks that actually create a different type of soil depending on what that parent material is. Igneous rocks, of course, are volcanic in origin. Sedimentary rocks are composed of many different fragments that have been transported. Good examples of sedimentary rocks include limestone, sandstone, and shell. And then we have metamorphic rocks that are formed either from igneous or sedimentary rocks, but then have been subjected to incredibly high pressures and temperatures over millions of years that change their structure and composition. we think about soil formation over time and the ability of the parent material to create a living soil, it's due to the accumulation and transformation of the parent material. It starts to accumulate first by the breakdown of the naturally present rocks through weathering. And as that weathering occurs over time, it forms soils into these different layers known to us as soil horizons. As these horizons become distinguishable, they develop into what are known as soil profiles. We have several different types of weathering that turns that parent material into an active soil. And first, it begins with the physical weathering, and that's actually just the physical breakdown, usually due to temperature and water kind of forming and expanding and contracting in the spaces of the parent material. Of course, we can see physical weathering over time. In this case, in the photograph, this is occurring over a short period of time due to human actions. This is some extreme erosion, probably a combination of stream and sheet as well as rill erosion to create this type of gully. This is kind of similar to what we saw really in the last ice age, very similar to the action of glaciers running through areas. And changing that parent material, kind of breaking it up, actually physically breaking it up. As I mentioned, this is due to human activities in combination often with heavy rainfall. So, especially thinking about what's happening right now with Hurricane Florence, any exposed soil can really actively erode, and we can really lose valuable topsoil. Of course, when we think about soil and water, actually thinking about natural bodies of water, soil is the #1 pollutant. We also have chemical weathering, and there are basically 4 processes of chemical weathering, beginning with dissolution, which is thinking about dissolution as an acid breaking down and moving minerals in the parent material of rock. We also have hydration. Think of that like hydration in us as well. It's adding molecular water, which changes the chemical form of the soil or parent material and allows it to be broken down more. And we also have hydrolysis, which is a reaction between a mineral compound and water that then forms a more soluble product, similar but slightly different to hydration, in that rather than just adding water, it's actually a reaction between the compound and water. And finally, oxidation, which you've seen, of course, in the form of rust on metals. Well, it happens in soil too, and it's just a reaction of oxides to the parent material. And often it actually can even look like rust in a soil. You can see oranges and reds in oxidized soils. The next big thing is climate. So rainfall is one of the big things that governs how soils are created. In areas where we have high rainfall, soils are often highly leached. Or also areas where the soils or parent material are very old. Like in the Appalachian Mountains, for instance. The oldest mountains on the planet have highly weathered soils. And generally, most of the soils in the eastern United States are highly leached because they're typically very old soils. Whereas the soils in the Midwest generally are much younger soils. Because of the age, we have lots of leaching, and that causes general soil fertility to be low, although it can be higher from place to place. And of course, they can still be productive by the addition of nutrients. It's the opposite in arid climates. They're not highly leached, and they tend to have an entirely different chemical component. Let's talk a little bit about biology. And when you think about the biology from plants first, both what type of plants naturally grow in an area and how those plants react with the soil. So first we think about the root system, and that causes some actual physical weathering itself by the roots actually growing into the soil. Generally 10 to 50% of plant dry matter is in the root system, depending on the plant, of course, and also the soil type. We all know that roots support and anchor the plant stem. They are also responsible for absorbing water and nutrients, usually both at the same time. And they also provide storage for food reserves in many cases. Think about the main roots and then root hairs and the root tips moving through the soil and exploring the gaps in soil particles. There's also actually chemicals in the roots that plants secrete chemicals into the soil to help the absorption of nutrients, also to help them compete with other plants, and to help roots actually penetrate soil particles. And as new roots form, old roots die off, and about half of the root system of the average plant is turned over in 1 year. Also about biology, we're thinking about the soil biology. And the soil is home to an incredible diversity of organisms, and what I really want you to examine is that they're from all 5 kingdoms. Of course, we have the plant kingdom growing in soil in the form of roots, also algae as well. We've got the animal kingdom working, larger macro vertebrates and invertebrates burrowing in the soil, as well as kind of mixing soils from lower horizons to upper horizons. We also have fungi, protista, and minera, which we think of as bacteria. And they're all part of a very complex soil food web that has profound effects on really all aspects of the soil. Bacteria are the most abundant soil organisms, and just like with people, we can have good and bad bacteria in the soil. They're incredibly important for decomposing and recycling of nutrients, as well as fungi. And really, bacteria and fungi are really the 2 most important parts of the living soil. Fungi are also responsible for breaking down soil and organic matter in the soil, as well as associating with plants, like we talked about earlier with mycorrhiza. There's also protista that provide food in the soil for other, and of course, animals as well. One big thing in soil is organic matter, and that's something that we really have to look at trying to govern in the soil, which is influenced, of course, by the climate itself, what plants naturally grow there. We think of organic matter as anything that was once alive that then becomes part of the soil and becomes decomposed within a soil. Organic matter is abbreviated as OM and is incredibly important for holding nutrients in soil. Next, we think about the topography, and generally with topography we're thinking of slopes. So with steeper slopes we have more erosion, more movement of soil, and with more level soils we have less, although it can still be prone to erosion. One big thing with topography and what can affect erosion is just vegetation. And ideally in agricultural production we want to keep the soil covered, whether that is with vegetation or with mulches, cover crops, whatever it is. If the soil is exposed, then it's more vulnerable to being lost. Also thinking about topography in terms of altitude affects different types of vegetation, and it causes soil to move. So looking at this mountain, and kind of think of the mountain as like a macrocosm, and kind of apply that same topography on the farm level as a microcosm. At certain altitudes and certain slopes, soil will move more or be more or less vegetated. Time, of course, is the great unifying factor of soils and their production. The creation of soils is all of these different factors together over time. When we think of hard to decompose rocks such as granite, more metamorphic rocks, they require millions of years to form soils from a parent material, whereas softer, more sedimentary rocks require much less time to form soils. When we're looking at the age of soils, generally those without well-developed horizons are young soils. And generally most of our young soils in the United States are in the Midwest. And they still have some well-developed horizons. But we can see young soils in many different places, especially in mountainous areas. Also altered soils that are altered by things like flooding or other natural disasters. So let's talk about horizons for a little bit and kind of just the basics of soil horizons. First, we have the topsoil, and generally the topsoil is all in this A horizon. The A horizon is generally the top 6 to 8 inches of most soils, although it can be much deeper in some cases, and in some cases it can be completely absent. Generally, the A horizon has the greatest biological activity. It is generally where the highest amount of organic matter in a soil is, which tends to give it the darker color. It's the most responsible for crop growth. Going down, we go to the B horizon, and the B horizon is often thought of as the zone of accumulation, where nutrients are kind of moving downward, but also different parts of soil texture are moving downward. Generally, color is lighter. There's less organic matter, but plants still grow here in many cases, especially deeper-rooted plants reaching into the B horizon. The C horizon is generally what we think of as most closely related to the parent material. It's generally the least weathered and has more rock in it, more parent material actually in there. And generally we don't have, especially with crops, many plant roots penetrating that C horizon. In reality, most soils are labeled differently. It's not just A, B, and C, but in this photograph we clearly see the A, B, and C horizons. We'll do a little lab kind of looking at soil horizons later on. Another huge part of soil and what leads to productivity of soil is just the texture of soil itself. And generally we're looking at soil texture as kind of the ratio, the different proportions of sand, silt, and clay particles in the soil. And when we're looking at measuring soil texture, we're going to actually break down sand, silt, and clay and look at the different components of each that really governs how productive a soil can be. In terms of size, you don't usually think about it, but sand is actually the largest of the soil particles that make up texture. And I like to think of sand as like this sand particle being like the size of the classroom that you're in. If the campus of your community college is a soil, a sand particle would be like the size of the classroom. A silt particle would be like the size of you or your chair sitting inside of the classroom. And a clay particle would be like the size of a freckle on you. So there's a huge variety in size between sand and clay particles. And each of these is important. The USDA created this nifty little soil texture triangle to try to determine what a soil would be classified as texturally. And generally in soil texture, we're hoping that we're kind of here in this lower center part. We would like to be a sandy, silty loam as the most productive soil. And that's based on the different percentages. So, we'll do a lab kind of looking at soil texture and reading it and looking at how we can use soil texture to determine productivity of soils and what we might need to do to amend the soils. This table just shows how texture influences the different soil properties related to crop production. So I would definitely recommend reviewing this table with representation to the upcoming quiz for this chapter. Texture also influences the way that a soil is aerated, what the air pockets are, where they tend to be, as well as the ease of actually influencing the soil through tillage. And we look at tillage as not just actually using a tiller, but thinking about how we generally prepare fields, the tilth of the soil, the relative soil texture and structure. So we influence that generally by a combination of plowing and disking and cultivating or tilling to influence the soil texture. Naturally, sandy or loamy soils would be much more easy to prepare and to till than clay soils. Again, the ideal agricultural soil is a fairly even mix of sand, silt, and loam, known as a sandy, silty loam. And does that soil really exist in your area? Maybe or maybe not. It does exist, for sure, in pockets, especially in more alluvial soils, areas where there tend to be movement or additions by water. Soil structure is a little bit different than soil texture, and really we're thinking about the arrangement of the different soil particles into kind of clumps, basically. And we call these secondary units aggregates, these clumps of soil. And they generally have specific characteristics such as size and form, as well as shape. So here's some kind of some descriptions, depictions, I should say, of the different soil structures. A being platy, B being prismatic, C, columnar, D being angular, blocky, E, subangular or blocky, and then F, granular. Which of these do you think we're trying to strive for with tillage? Well, if you guessed F, you're correct. Generally, we turn soils into more of a granular structure with tillage. And a sandy, silty loam tends to have more of a granular structure naturally. This granular structure can be good, but something that you might want to recognize there is that we can overdo it. We can definitely overtill over time creating things like hard pans and actually limiting soil productivity. Generally, there's going to be more pore spaces in a subangular blocky or angular blocky soil than there's going to be in a granular soil. And because of that, that's more areas for water to drain out or to be held, and also for air to exist. So in a granular soil, we've got to watch out, because the more we till, the more we create this granular structure, the more we tend to lose air pockets and water pockets, as well as making the soil more prone to things such as compaction and erosion. I'm looking at a more chemical property of soil. Let's look at the pH, which pH is literally thinking of the power of hydrogen. And it's the negative logarithm of positively charged hydrogen ions in the soil solution. Of course, pH can vary, usually between 4 and 10. We don't really have soils that are below a 4 or above a 10, and really plants cannot grow below 4 or above 10. But generally, a soil on a lower pH scale is more acidic, and on a higher pH scale is more alkaline or basic. And what we know as a sweet soil is a neutral, and 7 in pH is neutral. And generally, we want to keep our soils, ideally if we can, kind of right around 7, kind of in between 6 and 8 for the production of the widest variety of crops. And here's just a table looking at the soil pH range for the optimal growth of some cultivated plants. Of course, many plants prefer more acidic or more basic soils, but notice that we don't really have soils that prefer, or plants that prefer soils above a 7.5. We do have plants that prefer soils on a lower pH level, though. And if we're thinking about crops, think about where they grow naturally, and what those soils are like. So, for instance, blueberries prefer more acidic soils, and you're going to have a really hard time with blueberry crops if your soils are not acidic. So, pay attention to that as well. Another big thing about why most plants prefer kind of the neutral or sweet range there is because of the availability of nutrients. And this is looking both at macro and micronutrients. And as you can see, the greatest availability of the widest range of nutrients is right there on the neutral scale. Some nutrients are more available in acidic soils, and some are more available in alkaline soils. For the greatest range of both crops and nutrients, we're looking at right around neutral. And generally, when we're thinking about soil pH, the higher the rainfall, the more acidic a soil, lower, generally the more alkaline. And we can change that with different types of soil amendments. If we want to raise the pH, then generally we want to use things like lime. If we want to lower it, we usually use things that involve sulfur. Another important chemical property of soil is cation exchange capacity. And a cation is simply just a positively charged ion in its elemental or molecular form. So generally, clay and organic matter-filled soils are those that have the higher cation exchange capacities. The CEC is a very important chemical property of soil that really translates to the ability of a soil to provide nutrients to plants. Although you don't just want to look at cation exchange capacity alone. For instance, very heavy clay soils tend to have very high cation exchange capacities, but they don't have the greatest soil texture or soil structure, so they're not the best for growing crops. Back to the whole soil organism thing, look at the microorganisms in soil are extremely important for providing nutrients, and the different types of organisms present in the soil are going to depend on those different factors of soil formation, as well as the chemical and physical properties of a soil. One of the most important biological processes in natural soils is nitrogen fixation. And that's, again, just basically taking the nitrogen from the atmosphere and fixing it in the soil. And what we see pictured here is the roots of a legume. And you'll see these little nodules here, these little round areas. That's where the bacteria live and are actually fixing that nitrogen inside the plant. Legumes such as beans, in this case soybeans, many other legumes out there, and also some plants in the rose family do provide this nitrogen fixation. They can provide a little bit of extra nitrogen for other crops, but generally they're just reducing the need for nitrogen. Let's talk about the ohm, the organic matter content of a soil, which is really the main driver of soil biology, but also has profound effects on chemical and physical properties as well. Generally, when we're looking at organic matter, it's not only providing structure for the soil, higher cation exchange capacity, but it's providing some of the main nutrients for plants. And although these are not really listed as macronutrients, carbon, hydrogen, and oxygen, which are these organic molecules, are the primary components of plants. That's what makes the physical body of plants, the CHOs, and of course is what makes up sugars as well. When we look at organic matter, we look at its rate of decomposing. All organic matter decomposes. The organic matter percentage of a soil naturally changes annually, and that depends on the chemical composition of the soil and kind of what's going on with the climate as well. When organic matter becomes completely decomposed and becomes this kind of colloidal substance, we know it as humus. Not humus, but humus. It becomes resistant to further decomposition, but it also contributes very important colloidal factors to the soil in terms of structure and cation exchange capacity. So humus is very important in the soil. Of course, we have organic matter in fluctuation in soil as well. So it's starting to decompose. And that's really kind of based on the carbon to nitrogen ratio in the soil. We think about that in terms of greens and browns. The greens tend to be more nitrogen heavy, the browns more carbon heavy in a soil. And we need to add both. We need both carbon and nitrogen, but we need a lot more carbon in order for it to actually decompose and make nitrogen available. Again, talking about soil degradation, if the cover is removed, whether it's a natural disaster or just harvesting of crops, it makes the soil more susceptible to degradation from erosion and weathering, from wind or rainfall or water runoff. And generally, across the country and really across the world, we're losing soil faster than it can be created. We're talking about topsoil is being formed, 1 millimeter, every 100 years. So and we're losing it rapidly, especially with big rain events, big storms on uncovered soil. So one of the big take-homes for soil health, keep it covered. If we lose that A horizon, then we really lose most of our crop productivity. Plants just can't grow. Crops can't grow as well in B horizon. And that's it for the presentation for today. I'll be putting up the quizzes for Chapter 3 and 4 today as well. And I'll give you guys a week to take those. They will be timed. You'll be given an hour for each of those quizzes. So review that. If you guys have any questions, comments, or concerns, feel free to email me. Also, stay tuned. I'll be posting the lab soon, and we'll talk more about those on Wednesday. Hope you all have a great day.